In this video, we're going to take a look at for which substances the ideal gas law tends to work well or not so well as under what conditions the ideal gas law tends to work well or not so well. So we're talking about sort of when we deviate from that ideal behavior that we've sort of come to expect from gases at this point. So in general, gases tend to behave most ideally when the assumptions of kinetic molecular theory are closest to being true. That should make some sense. If kinetic molecular theory is sort of where the ideal gas law comes from, the ideal gas law is based on making these assumptions when they're closest to true. Ideal gas law gives you the best results, that your calculations will match experimental values most closely. So, sort of two different ways we want to be able to think about this. First is that some gases, some substances are just inherently more or less ideal, that they behave more closely or less closely to what we would consider to be an ideal gas. So for comparing different substances, the main two assumptions that are going to vary in their truthfulness from substance to substance, as well as for different reaction conditions, is the particles are infinitely small assumption and the no forces of attraction between gas particles assumption. So there are kind of two factors of molecular structure that we need to be able to think about here. So first is size. That one of our assumptions for the ideal gas law, or one of the assumptions for kinetic molecular theory, is that particles are infinitely small. So the larger a molecule is, the less ideal it is. The smaller it is, the more ideal it is. So smaller molecules or smaller atoms behave more ideally because they are closer to being infinitely small. They are closer to occupying zero volume. Larger gas molecules, less ideally because they're actually taking up a larger proportion of the space in your container. The other one is the no forces of attraction, is one of the assumptions that we make. So the closer that is to true, the more ideal your gas. So the weaker the intermolecular forces, the more ideal your gas, more ideally your gas will behave. Because these are closer to zero forces of attraction. So, for instance, if we wanted to compare which of these substances is likely to behave more ideally, let's say argon or xenon, two different noble gases. They are going to be pretty similar in intermolecular forces. They're both just a single atom, so they're nonpolar, so all they have is London dispersion forces. We know that London dispersion forces do vary in strength with size, and size is also one of our deciding factors here. So if we look at our periodic table, we see that argon is a couple rows above xenon, which means that argon is going to be smaller. Also means it's going to have weaker London dispersion forces. So the one that would behave more ideally in this case would be argon for both of these reasons. It's a smaller atom than xenon, and also has weaker intermolecular forces. So both of those assumptions, infinitely small, no attractions, are closer to being true for argon than they are for xenon. So we would expect that calculated results from the ideal gas law would more closely agree with measured results in the lab for argon. In reality, both of these are pretty good. Both of these are pretty close to ideal, but argon is a little bit better. One more example for this. Actually, same question, we'll just do a different pair. H2S or H2O. So this one, close enough. So these two things are going to be pretty similar in size. The H2S would be a little bit bigger just because sulfur is a larger atom than oxygen, but they both have 3 atoms, so they're both going to be similar in size. And then the difference really is going to come down to the intermolecular forces. So we know that water can hydrogen bond So this one is going to have, so water is going to have much stronger intermolecular forces. Which generally means that it's going to behave less ideally. So H2S would be the more ideal of these two substances. We can also compare the same substance under different conditions and how well the ideal gas law sort of works for different sets of conditions. So generally speaking, the ideal gas law works well, or works best, when your gas molecules are really, really spread apart, gas particles. So we said that the reason why particles being infinitely small was a pretty good approximation was because they're so spread out, because the molecules are so spread out. There's really a lot of empty space, and the amount of space taken up by the particles themselves is a very, very small fraction. That's only true when your molecules are actually spread out with lots of empty space between them. And then similarly for the intermolecular forces, we said that no forces of attraction was a pretty good assumption because gas particles are far apart. They just don't get the opportunity to interact very much. So the ideal gas law is going to work best when your particles are spread out a lot, regardless of what those particles are. So particles tend to spread out when the pressure is low and or the temperature is relatively high. Those are the two types of conditions that tend to lead to particles wanting to spread out. If your pressure is low, that means you don't have a lot of collisions going on in your container, so particles are going to be relatively spread out. If your temperature is high, that leads to your particles wanting to spread out if they have the space available to them. So depending on kind of what's changing, what's being held constant in your system, low P or high T, one or both of those being true, tends to lead to the most ideal conditions possible for whatever gas you happen to be working with. So you should be kind of vaguely qualitatively aware of when the ideal gas law works well, both for like what types of substances it works well, and under what types of conditions it works well. Note that typical lab conditions are considered a relatively low pressure. So 1 atmosphere, standard atmospheric pressure is considered relatively low, and standard room temperature is considered relatively high. So under normal lab conditions, the ideal gas law works pretty well for most things, is why we teach it, is why we use it, unless we absolutely have to use one of the more complicated gas laws. If we're working at a super high pressure or really, really low temperatures, then things can get a little bit weird. But other than that, the ideal gas law works well most of the time.